Hello again. In this video, we're going to do two things. We're going to first reflect t through the vertical x2 axis, and then we're going to rotate that point 90 degrees or pi over 2 radians. And they didn't say, but I'm going to rotate it counterclockwise. So I'm going to take our standard E1 and E2. We can look at this region. And what we're going to do is we're going to first reflect it through the x2 axis. So if we did that, E2 would remain the same. So let's call that T. Actually, since it's not our end result, I'm going to call it S of E2. And then this point, I'm going to reflect to over here. We'll call that S of E1. And that's going to be negative 1, 0. Now we're going to do it again. So first, this was S. Now this is what I'm going to call our T. So we're going to now rotate pi over 2 radians clockwise. So this point right here is going to rotate to that point. And then this point is going to rotate down to this point. So you'll have a box like this. So I first reflect, then I'm going to rotate 90 degrees. This point right here is going to be T of, really, S of E2. That's what that is, if you really want to know. And it's negative 1, 0. And then this point is going to be T of S of E1. It's a composition function. And that's going to equal, ran out of room, 0, negative 1. So our standard matrix, which, by the way, is the question. If you look at the beginning, it says for exercises 1 through 10, assume T is a linear transformation, find the standard matrix. So I added that here of T. So A is going to be T of T of S of E1 and T of S of E2. So that's what you do when there's more than one. So A, in our case, is going to be, E1 would be 0, negative 1, and E2 would be negative 1, 0. So when you do more than one thing, notice how you almost didn't even need this at all, right? You just really care, where does this end up? And again, we reflected it, did nothing, and then we rotated it, so end up there. Where does this end up? We reflected it, and then rotated it, so it ended up there. It's the end result for each original E1 and E2. Let's look at another method of doing number 10. The same question. We are looking first, we want to reflect points through the vertical x2 axis, and then we want to rotate through pi over 2, and I'm going to do, again, counterclockwise as above. The standard matrix for a reflection through the x1 axis is negative 1, 0, 0, 1. You can see that right here. It's just the S of E1 here and the S of E2 there. Let's call that B. Therefore, S of X is, we know, the first, I drew the picture up there of what we had before, is just BX. And you can also look this up in our table. We know the standard matrix for a pi over 2 rotation counterclockwise is, well, we had a formula for that. is cosine of phi, sine of phi, minus sine of phi, cosine of phi, where phi is pi over 2. Which, by the way, cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of negative pi over 2 is negative 1. And sine of pi over 2 is 0. Let's call that C. It turns out that our standard rotation for this situation is going to be in the opposite order, C times B. Why? Because we're looking for t. Oh, by the way, t of x, we're doing this one, right, is we know cx. And what we have here is a composition. Going back over here, we have t of s. So I'm going to call this t of s of x, but s of x is bx, so it's going to be t of bx. And if I plug that into t, right there, I get c of bx, which is just cbx. Therefore, A is just c times b. So let's try it out. So we just take the rotation matrix, pi over 2, counterclockwise rotation matrix, and multiply it by the reflection matrix on x2. What would we get? We're going to get another 2 by 2, aren't we? First row, first column. Now we have not multiplied matrices yet, so this is going to be the next section. 2.1 will explain how to multiply a 2 by 2 times a 2 by 2. But I will just tell you now that a 2 by 2 times a 2 by 2 is going to be in a 2 by 2. So again, these inner sides have to be the same, and it could be the outer. So it's going to be the same thing as a vector. So you take this first row times this first column, and what do you get is 0 times 0. And then to get the second entry, it's going to be just like the vectors, it's the second row times that first column. So you get a negative 1 plus 0. Now to get this, you're just going to use the second column. So you take the first row times the second column. First row times the second column is going to give you the first row and second column here. So that would be, right, 0, negative 1. And then finally, the last one is the second row, second column. So that would give you the 0. Is that the same answer that we had? Let's look. There it is. Yep, it had negative 1s along that diagonal. It sure is. So let's check it. Let's let u be, I don't know, 1, 2 again. And let's see if that first reflects, what was the question? First reflects, through x2, and then rotates pi over 2 counterclockwise. So let's just take t of whatever, let's just multiply. Let's just take this end result and let's multiply it by 1, 2 and see what we get. So that would be 0, negative 2, and then, right, first row, the column, second row, and that first column, that would be negative 1, 0. So let's see if that works. So we have 1, 2. That's my vector u. And then we're going to get negative 2, negative 1. That's the end result. So let's see. If I first reflect it through x2, I would get this point right here. Dot, 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 dot. And then I would rotate it 90 degrees counterclockwise. I would indeed get that vector. So this means we can take any point and almost do anything that we want with it. By either multiplying, we can do it by multiplying each standard vector that you know, right, in the opposite order that you're going to do something in. Or you can just do the method 1, which is a nice, great method. Just look at the beginning to the end, what happens, and that is going to be your end result. So what does this all tell us? Well, this tells us that this is a great application for computer graphics. What is computer graphics? Computer graphics are images displayed or animated on a computer screen. And as you can see, the math of computer science is connected directly with matrix multiplication using transformations. But just to warn you, what we learned in this section is limited because moving some points on the screen is not linear, such as vertical shifts, for instance. You can check out section 2.7 for more info, which is on computer graphics.